Okay. Okay, so I'm somewhat disappointed. My battery just died on halfway through the last video, so I'm starting over. Hopefully I've got my spiel down this time. So for the robotics project that we did, we built a 3 revolute joint parallel manipulator, planar manipulator, with the first joint actuated, which you can see here. It's actually powered right now, so I can't turn them. The joints are actuated by BMS-620 MG servos. They have 132-degree rotation. The feasible space is approximately, as I'm tracing it, I have a picture of it so I can show you, but it's not actually able to reach the entire space it could reach given the geometry. It's not actually able to reach that due to the limitations of rotation, limitations of actuation of the servos, not rotation, of actuation. They can rotate farther than they can actuate. So this is controlled using an Arduino. The Arduino basically listens on the serial port to MATLAB. MATLAB performs inverse kinematics given defined geometry of the manipulator. The inverse kinematics determines the angles the angles of the joints, and it also determines the angles, it determines all the angles for the joints. So there's a theta 1, which is deflection of this joint from its zero configuration. There's theta 2, which is deflection of this joint from its configuration, and theta 3, which is deflection of that from its zero configuration. And you have a theta 1, theta 2, theta 3 for each arm. You don't actually need all 3 angles. You only need the first angle to actually actuate it. That's the angle, or you need the angle which represents your actuated joint. That is what you need. So our joint is the first joint, and that's what MATLAB is actually sending to the Arduino. MATLAB opens a serial port on COM4 and holds that open while it performs the inverse kinematics. Then it does some mapping of the angles from inverse kinematics to the actual angles we need to write on the servos, and then it writes those angles to the servos over the serial port and listens to the serial port for the Arduino to confirm it received the command. So I guess let's demonstrate this working. I have, what do I have? I have 3 different examples here. This one is writing out a rectangle. It's going to look a little weird. And let's do that again in case you missed. That's writing out a rectangle if you follow it. It goes to the center first because each time the code is run on MATLAB, it opens and closes a serial port, which resets the Arduino. And when it resets, the servos go to center, which 0, 0 is defined with the task coordinate. It's defined off the task coordinate. So 0, 0 is around up here. It's 0, x, or y, 0, phi. Phi being the rotation of your plate. We also have an example for a star. It'd be great if this was actually writing it so you could see with a Sharpie, but I didn't think of trying to fix a Sharpie down below. That would have been good for the video. I wish I'd done that. Okay, so this is ready. This is going to write out a star. And again, it goes to center first, as you see. It goes to center before actually writing out what it's commanded to write. And the final example is smooth rectangle, which is just a series of points, so it's a finer resolution, which makes it a bit slower also. Smooth rectangle for your viewing pleasure. And let's do that again. It's going to go to center, and then it's going to start writing from the bottom corner. Okay, so that just finished. What should we talk about next? Let me check my script for a second. I don't remember if I talked about how it works. I know I said inverse kinematics. I know I said MATLAB. And then MATLAB writes to serial line to the Arduino. Okay, limitations. The manipulator as constructed is not machined as well as it could be. If I was a professional machinist, I'm sure I could have built it much more rigid, or if I'd had a bit more time, that would have been good too. As you can see, they rotate around a bit, or wiggle. Also, because they're not rigid, the center plate isn't actually, it should have a defined position given the inverse kinematics. It should not be able to rotate. It shouldn't have two different solutions given a phi and an xy. The joints also, they are not pinned as best as they could be. These, if we can focus, these use screws rather than actual pins. I didn't have any pins on hand and couldn't find any small enough, and I couldn't machine any out of aluminum because they kind of bend on the lathe when you try and do that. Aluminum's pretty soft, so it's hard to machine to that diameter. I believe it's 9 millimeters, not 9 millimeters. It's a 9/100th of an inch, I believe. Same thing on the center. While these screws aren't even the same thread, these are M3 threaded screws. These, I believe, are the closest English equivalent to that. I don't remember the size. It's really close to M3. These screws are actually, they're acting a bit more like pins because I got a smaller diameter screw. It doesn't rotate. The arms aren't actually rotating on the threads. That's another thing about using screws. When these rotate, the arms are going up and down the threads slightly, so it's not as precise as it otherwise could be. The center platform. Building that unfortunately did not turn out as precise as I wanted it to. I believe it's about 6 millimeters to a side, or close to 6 millimeters to a side, or 60 millimeters, 6 centimeters to a side, nearly. Except when I cut it on the bandsaw and then sanded it down so it wasn't sharp, it kind of takes off some of the it took off some of what it measured, so it's not precisely a equilateral triangle. It's not precisely as defined in the code. So you can actually see in the code, even the angles from the inverse kinematics, they're off by maybe a degree or two, less than 2 degrees. It's usually about a degree if they're off. That's because just errors in the geometry as defined. The geometry as defined in the MATLAB code doesn't necessarily represent exactly the geometry as it's constructed, so that creates some errors in the calculated angles. Let's see what else. I talked about how the servos can't rotate all the way. That limits our feasible space. There's actually a very good simulator available. I believe it's at Parallel Mic. Let me bring that up. Yes, there's a simulator for a 3 degree of freedom, exactly the same 3 RRR planar parallel robot, exactly the same as what we have here. It's available at Parallel Mic. parallelmic.org. You can find it there. And you can, if you'd like to build something similar, you can actually compare your angles from the inverse kinematics to the angles from that simulator. So it gives a nice reference check when you're building. Something to talk about here. Okay, so when you do the inverse kinematics, there are 2 solutions. There's the elbow up and the elbow down, or elbow left, elbow right solution. This is using the elbow up configuration. If it was the elbow down, then this arm would be connected at the other side, which I can't make it reach at the moment, but you see it would be connected over at this end instead. That would be the elbow up solution. or I'm sorry, the elbow down solution. We're using elbow up. That's a nice thing about these arms too. They came machined just for the servos. And we can adjust the position of the arms if we wanted to, and that would change the geometry. And that's actually why we chose the servos, was it made it, we didn't have to machine the arms, which was a pain. I wish I knew how to machine better than I do. The arms have they have a spline. It matches the spline for a Futaba servo, which is 25, I think 25 clicks in it, like 14.5 degrees per. So it's Futaba splines. That's why we chose that, so that we could use the arms. And that data sheet did not have any mention of limitations for the servo rotation. So shame on you, Hobby King. You should please get your data sheets together. I was very disappointed that these don't actually rotate 180 degrees. If the task position is commanded to a position that's actually outside of the feasible space, where it's not able to reach it due to one of the servos can't rotate that far, or it's constrained by the arms, then when you do inverse kinematics, you'll end up with imaginary solutions. You'll end up with imaginary angles. So what you can do to limit your actuation to be within the feasible space is check to see if your servo angles are real. If any of your servo angles are imaginary, then it is outside of the solution space. Let's check the list here. Limitations, how it can be improved. Okay, another solution we could have used rather than using servos is motors. We did not use motors because motors do not have any sort of feedback. If we'd wanted to use motors, we would have had to use an encoder also, something like that. That's actually a relative encoder. We would have needed an absolute encoder so that we know the position should, say, power be turned off in the middle. If we'd had absolute encoders, we could have used stepper motors to actuate instead of the servos. Servos have a potentiometer built in, which, as the angle is as the servo is rotated, it's rotating the potentiometer, so that's changing the resistance it's reading, and you're getting feedback based on that. And since the potentiometer is limited in how far it can rotate, you have essentially an absolute encoder with the servo. What else can we talk about? I have nothing else to talk about, I don't think. So, anything else that could be changed? Okay. For the servos to actuate, we also had to use external power. Thank you, Amazon. Which gives, I think it's 3 amps and 5 volts. It's regulated power also. Do not use unregulated power with your servos. You will burn them out. Unless you use a voltage regulator, which then is regulated. I guess I can give a quick show of the code. Actually, no, I won't do that. If you have any questions about the code or the kinematics, I'll provide links on the video so that you have those available for your own projects. Don't fall over. Please don't fall over. Paper. I can talk about the paper. The inverse kinematics we used was the sine-cosine approach, which is outlined in the paper by Robert Williams and Brett Shelley, Inverse Kinematics for Planar Parallel Manipulators. You can find that if you do a simple Google search, or I will provide the link for you lazy people out there. That paper provides the general solution for all 343 different types of planar 3-joint manipulators. You can have revolute or prismatic joints, and each joint could be the actuated joint. So you have 343 different solutions. The solution provided there was the RRR, with the first revolute being actuated. And that was used because it provides definite... Give me a second for my notes. I'll just write that. Yes, there's a paper by Lipkin and Duffy which suggests the... what was it? The cosine sine solution uses tangent 2 in MATLAB, if you use MATLAB. It avoids the indeterminacies that occur with the tangent half-angle solution used by psi. There's a discussion of this available in the paper. A control approach, I hope that's not backwards. A control approach of a 3 RRR planar parallel mini robot by Balan and Stan and et al. We used the sine-cosine solution because it avoided those indeterminacies. That's why we used that. I'm pretty sure I discussed the two different solutions. You have the elbow up, elbow down. If I didn't, then comment on that, I suppose. I'm jittery, I drank coffee. I can't handle coffee. I believe that's it. I don't have anything else on my list. So, if you have any questions, ask, message, or do your own research. Teach yourself. Google. Google knows everything. And I suppose that's it. It was a cool project. I learned a lot in this project. The project for robotics for Professor Wynn, which I probably won't pass.